SF 5.5 Introduction to Integrations. So in today's video, we are going to go over integration and how to find the antiderivative of the certain functions. So now if you look at the section A, we have a definition for the integration. So for the majority of the operations that we have discussed in mathematics, we'll always like to know how to do it in reverse, right? So with this section of the curriculum, we learn about the opposite of the differentiation known as integration and anti-differentiation process. So when we have a function, and if we differentiate this function, we get the derivative. So when you go from function to the derivative, the process is called the differentiation function. And that means when you go back from the derivative to function, its original function, we go through integration process, or we also call it anti-differentiation process. So if you look at this box here, the notation part, the notation for the integral of the function f of x uses this sign here along with the sign dx. Okay, so this music note kind of looking sign is sign for the notation for the integration, and dx simply means with respect to the x. So the integration rule is quite simple. You just have to think like we're like going back. We are reversing the differentiation rule. So for example, if we have a function f of x, which is equal to x to the power of n, then when you differentiate this, we always move n to the front, right? And x to the power of, we subtract minus 1, right? Or we subtract 1 from that power, right? And this is your simple power rule. So same thing applies to the integration of a function. So means when you integrate a function or the derivative of function, what we need to do is we simply add 1 to the power and divide the whole thing by the new power, n plus 1. And we need to add the constant that we might have cancelled it during the differentiation process. So this is your integration rule. So now let's try to apply this into an actual question. So if you look at the next page, we have example number 1 where we have a derivative of the function f of x, and it is equal to 6x squared plus x plus 7, and we need to find function f of x, the original function, right? So we're going to use the integration, the rule, where we have to do f of 8x to the power of n times dx is equal to 8 times x to the power of n plus 1 divided by the n plus 1 plus c. We're going to use this formula to integrate this function, get this derivative. So what we need to do is the original function is same as, so we add 1 to that power, right? And divide the whole term by that new power. And then we do same thing for the next one. So x actually has a power of 1, right? So we do x1 plus 1 divide whole thing by that new power. And the 7 is actually same as x to the power of 0, right? So x to the power of 0 is equal to 1. And so 7 times x to the power of 0 is equal to 7. So means we can actually rewrite that 7 as 7 times x to the power of 0. Means we can add the 1 to the power and divide the whole thing by the new power. And we finally have to add our constant. Then it is equals to 6x to the power of 3 over 3 plus x to the power of 2 over 2 plus 7 times x over 1 plus c, and it is equals to 2x cubed plus 1 over 2 times x squared plus 7x plus c. Then let's try the example number 2. So now we need to find the original function of this function here, or we need to integrate 10x minus 6 square root x dx. So we need to integrate this equation, okay, and that means this actually the equation part, the function part, is actually we can rewrite it as a 10x minus 6 times x to the power of 1 over 2 dx, right? And this form is much simpler to integrate. So when we integrate this is equals to 10 times x to the power of 1 plus 1 divide whole thing by this new power minus 6 x to the power of 1 over 2 plus 1 divide the whole thing by the new power. And we have to identify that constant that might have disappeared from the original equation, right? Then we can rewrite this equation as 10 over 2 times x to the power of 2 minus 6 times x to the power of 3 over 2 over 3 over 2, because 1 over 2 plus 1 is 3 over 2, and plus c. And this gets simplified, and now we have our final equation, 5x squared minus 4 times x to the power of 3 over 2 and plus c. Okay, so far we have tried to find the antiderivative of these certain functions with that unknown c, the last part, the constant, right? So now what we're going to do is we're going to try to find that constant at the end of the integral. So if you consider that any constant disappears when we differentiate, okay, then we are integrating. So we must write that possible c at the end in case there was any constant in the original equation. So we want to find this mystery constant, then we must know a set of coordinates. So means to find that mystery constant, you will always have a set of coordinates given, or you will have to find this set of coordinates prior to this part, like integration part. That so you can find that original functions. So let's look at this integration process. Again, I have put these steps or processes into 3 steps. Okay, so let's use the example from example number 1. So example number 1 was saying that we have a derivative of the function f of x that looks like this, and we need to find the function f of x. And from the example number 1, we have integrated this function, and we have found the original function as 2x cubed plus 1 over 2 x squared plus 7x with that mystery c at the end. Okay, so once you're done with this process, you're like almost done, right? We just have to find that unknown c at the end. So to calculate the unknown c, you will always have a set of coordinates given. So in this with this example, let's say that x value is equal to 1 and y value is equal to 10. So once again, you will either always have the set of coordinates to use to find the last part, or you will have to calculate that certain coordinates, or like this possible coordinate to find that last part, the constant, prior to doing any of the integration process. So it really depends on the question or how the question is set. Okay, however, to find that unknown c value, you always have to use a set of the coordinates. So here I have x value equals to 1, y value is equal to 10. Once you have a set of those coordinates, you just have to substitute them into your equations like this. And you solve for that Mr. C. Okay, so you will have a 2 plus 1 over 2 plus 7 plus c equals 10. That means your c value is equal to 1 over 2. Okay, so once you have found your unknown c value, you just simply have to plug that value into the function and rearrange it if needed. So means you just simply need to plug it back like this, and you're done with the finding the original function. Then let's try the example 3. Okay, so example 3, if we have dy over dx equals to 3x squared plus x, and y value is equal to 10 when x is equal to 1, we need to find the function y, right? So dy over dx is just another notation for y prime, right? So y prime is 3x squared plus x, and we need to find the original function y. Okay, so we're going to go through the integration process. So we do 3x squared, we add 1 to the power and divide the whole term by that new power, and we do same thing for everything, right? Every single term. And we have to add that Mr. C, the constant at the end. Then we get the function y. So function y is same as 3 times x to the power 3 over 3 plus x to the power 2 over 2 plus c, right? Then we know that y is equal to 3, or let's just simplify that right away. Okay, so y is equal to x cubed plus 1 over 2 times x to the power 2 plus c. And since we need to find that last part, we're going to substitute 1 into x and the 10 into y. Okay, then we have a 10 equals to 1 to the power 3 plus 1 over 2 x to the power 2 plus c. Then we need to simplify this again, and then c value is equal to 10 minus 3 over 2, which is equals to 17 over 2. So we can say that our function y is x cubed plus 1 over 2 x squared plus 17 over 2. And that's how you integrate. Okay, now let's try another example. So when you look at the example number 4, you can see that the lowercase f, when you integrate the lowercase f, it is equal to uppercase function f, or f function. And then we know that lowercase f function is equal to 15 times z to the power 4 minus 10 times z to the power negative 2. And we know that when z value is equal to 2, our uppercase f function has the value of the 73. Okay, and we need to find the uppercase f function. So when you have a lowercase f of z, when you integrate this, okay, it is equal to uppercase f function. And then we know that lowercase is same as 15 z to the power 4 minus 10 times z to the power negative 2. And we need to integrate this in terms of the z. Okay. Then when we integrate this, which is equal to uppercase f, it is same as 15 times z to the power 4 plus 1 over 4 plus 1 minus 10 times z to the power of negative 2 plus 1 over negative 2 plus 1 and plus c. Okay, then this simplifies into f of z equals to 15 over 5 z to the power of 5 minus 10 times z to the power of negative 1 over negative 1 plus c, and which simplifies into 3 times z to the power of 5 plus 10 times z to the power of negative 1 plus c. And we know that when z value is equals to 273, right? Then we can solve for the c, which is equal to 73 minus 3 times 2 to the power of 5 minus 10 times 2 to the power of negative 1. Okay, that means this is equals to minus 28. So our original equation for the uppercase f function has the equation of this. Okay, so this is the end of the indefinite integrals, and we will discuss more about the definite integrals next class, and also in essay 5.11.